All right, this is part 2 of our lecture on integration by parts. We're just going to get right into a third example. I'm going to assume you're comfortable with part 1. With the basic integration by parts formula, we'll be looking at a kind of a more challenging example here in example 3. Okay, this is a standard question every student that goes through Calculus 2 encounters in some variation. This is a kind of a classic. It's an integral question that I call or summarize as integrating without integrating. Now, if you make an attempt at this, it'll still be a little bit complicated. Maybe you encountered this before, but we're going to solve this in some sense. We're going to integrate without integrating. What does that mean? I'd like you to make an attempt at this. There's going to be something cyclical here. Integrate by parts twice, and you should find something peculiar happens. So pause the video, give yourself an attempt at this. One thing for me to show you a result, but another thing in mathematics for you to experience it on your own. So pause the video, give yourself several minutes to work out integrating by parts twice. We'll check in a few minutes. Welcome back. Let's go through the first integration by parts. There's really not a wrong choice here for U or dV, just as long as you're consistent. So for ease of calculation, I chose U as e to the x, since differentiating that is very simple. And I chose dV as cosine, since the antiderivative of cosine is just sine of x. There's no extra negative there. So this is a simple choice. Maybe you chose your U as cosine of x, your dV as e to the x dx. That could be an equivalent choice. It wouldn't matter for the question, just as long as you're consistent. So here we're going to choose U's as the exponential functions, dV's as the trig factors or trig functions. All right, complete your quantities, du and v, and we arrive at this result. The integral of e to the x cosine of x, our original integral, equals uv, e to the x sine of x, minus the integral of v du, the integral of e to the x sine of x. Now this looks very similar to our original integral. It's not quite the same. There's a sine term rather than a cosine term. So we can integrate this by parts again for the second time. Okay, what could go wrong? Let's go ahead and integrate by parts the second time. Here we'll be consistent. We'll choose u as the exponential function, dv as sine of x. Okay, be careful. Notice we have a minus in front of that integral of e to the x sine of x. So put brackets or parentheses around that, so that way you don't lose track of the negative. If a student makes a mistake through this or a similar question, it's likely due to a sign error. All right, so complete your second integration by parts. Use brackets around that integral, and then apply the integration by parts formula to the integral in brackets, the integral of e to the x sine of x. Okay, so it looks, well, like we've integrated by parts twice, and the original integral came back at the end there. Now, fortunately, we can recover. We haven't made a mistake, but if we were to repeat integrating integration by parts, we wouldn't really be getting anywhere. Every cycle of 2 integration by parts, we would just get back to basically where we started. Now, what saves us is if we're careful with the signs here. So let me open the brackets, the parentheses. I'll distribute the minus in front, change all the signs, and we arrive at this result. Now, before you proceed, make sure you're comfortable with all the signs. How do we actually recover here? We can't keep integrating by parts. We're just going to go in a circle. How we recover is we're going to look at this equation Notice I kept the left side, the integral of u dv. Recall at the start of this lecture, we mentioned to keep in mind the precise and proper formula. The integral of u dv equals uv minus the integral of v du. If you remembered or used the integration by parts formula as just the right-hand side, uv minus the integral of v du, you would miss this equation, which will allow us to solve for the integral. So again, just keep that in mind. I advocate remembering the left side of the integration by parts formula. Often forgotten or overlooked, the left side is the integral of your choices, the integral of u dv. All right, with that out of the way, how then do we complete the problem? We're just going to algebraically solve for what we're interested in. We're interested in the integral of e to the x cosine of x. So just solve this for the integral. Add that integral from the right side to the left side. At this point, we can combine like terms. The like terms here is or are that integral of e to the x cosine of x. We have something added to itself that'll give you 2 copies of that like term, 2 copies of the integral. How we solve for the integral, getting the integral by itself, like we would solve for x, just divide by 2. And like magic, here we solved algebraically. We never actually completely went forward by integrating, hence integrating without integrating. We get our antiderivative. Divide by 2, and we get our antiderivative for e to the x cosine of x as 1/2 e to the x times sine of x plus cosine of x. The 2 terms on the right-hand side above, I factored the exponential out from those two terms. Standard practice. Okay, this is again a standard example. It shows you some of the peculiarities with integrating by parts. It is possible, like in this example, you might integrate by parts once or several times. The original integral comes back, so we get an algebraic equation that we can solve for the integral. All right, now this was a simple example. Many of you might be moving on to Calc 4 differential equations. This integral typically pops up there with something called Laplace transforms. So let's take a look at some formulas that might be useful if and when you reach that course. And here are the typically stated integral formulas. The integrals for e to the ax times cosine or sine of bx. A and b are interpreted as constants. Now, right now, I'm just stating these so that you're familiar with them. They're just going to be useful integral formulas. How you can prove them is exactly like what we did in example 3. Integrate by parts twice, and then algebraically solve for your integral. Here it becomes a lot more complicated due to the factors of a and b, which would either come down or reciprocate with differentiating and integrating. These take a lot more care, but if you are up for the challenge, try to prove these integral formulas by integrating by parts twice and then solving for the integral. If you're successful with that, if you can kind of get through this pretty quickly and straightforwardly, you are in great shape not only for this course, but what comes next. Okay. So let's leave that example behind. If needed, go back and rewatch, pause at any point to fully understand what we're going through. I'm trying to take my time through this lecture since it's an important topic. Let's go ahead and get to some related ideas. Integration by parts and how it works with inverse functions. All right, so the typical inverse functions we're going to consider first are the inverses of exponential functions, logarithms, since you're all experts on pre-calculus. And then also from pre-calculus, each trig function has an inverse trig function. So the standard inverse functions we'll be dealing with within the calculus sequence, the ones that are kind of a fundamental importance that pop up so much, are natural log of x, inverse sine of x, and inverse tangent. Now what I'm stating here are not integrals of them, or those functions, but they're derivatives. Why, right now in Calc 2, when we're talking about integration methods, do we need to recall basic derivatives? Well, think how we apply the integration by parts formula. We choose u, but calculate du. We have to differentiate u to get du. Now, why I'm mentioning these differentiation formulas is, notice when you differentiate those expressions, the derivatives are no longer inverse functions, but algebraic expressions. So in some sense, if our choice for u were natural log of x, inverse sine of x, or inverse tangent, the derivative becomes simpler. There's no more inverse function. Okay, so what we're summarizing here is how we're going to choose u. We'll advocate to choose u as the inverse function. Typically, that leaves dv as just the differential dx, which is fine. If dv equals dx, v is just x. All right, let's go ahead and apply these ideas to example 4. Before we get to that, just on on topic with inverse trig functions, since we haven't used it in a while, here we have an integration formula that gives inverse tangent. Now be careful, here the answer or antiderivative involves inverse tangent of x over a. What we'll be looking at in example 4 is integrating inverse tangent. So inverse tangent will be on the left side within the integral. All right, here is example 4, 2 parts. They're somewhat straightforward, but your initial choice for u and dv might be a little confusing. So what we just reviewed, we'll advocate choose u as the inverse function, choose u for part A as natural log of x, and then for part B, choose u as inverse tangent of x. That leaves then dv as just dx. Pause the video and see if you can complete these. Part A is straightforward. Part B is a little tricky. We'll check in a few minutes. All right, welcome back. Let's go through part A together. So we mentioned we're going to choose u as the inverse function. So we'll choose u as natural log of x. Make sure you're on top of your basic derivatives. The derivative of natural log of x is 1 over x. If u is the inverse function, that leaves dv as being just dx, a standard choice then. All right, if dv equals dx, that means v must have been x. Now we have all of our pieces. Part A here is straightforward. Notice what happens when you multiply v by du. 1 over x times x cancels out to 1. So apply your integration by parts formula. This original integral equals uv minus the integral of v du. So we have here just the integral of dx. All right, at this point, we're basically done. Integrating dx, or 1 dx, just gives x. And we arrive at our antiderivative for natural log of x. You didn't mention back when you first encountered antiderivatives what an antiderivative for natural log of x was, perhaps back in your Calculus 1 course. The reason for that is, as we see here, we need the tools of Calculus 2 integration by parts to derive or prove this antiderivative. So natural log of x doesn't have a basic antiderivative, but it requires an integration method, integration by parts, a standard topic for your typical Calculus 2 course like ours. All right, now before we move on to part B, this is a good time just to clear up some notation. Notice with our choice of u and dv, that led to v being x. Now, what I wrote down with our choice of u and v, I switched the order. We have it stated as uv. We should write it as ln of x times x. But I switched it and wrote it as vu, x, ln x. The reason for that, you can kind of see down there in the remark on notation. It's standard, but certainly leads to some confusion to write that product as ln x times x. I see even the best students, probably even myself if I'm going too fast, accidentally confuse and mistake that for being interpreted as x times x. Be careful. We follow order of operations the way when we kind of write the function name in x side by side there, like ln x, we interpret x as being plugged inside the function natural log of x. So if you're going to write it in that order, natural log of x times x, use function parentheses, natural log of, in parentheses, x times x. All right, so just be careful with that. You're probably okay on that, but calculations could go pretty quick, and again, even the best students can make this mistake, from time to time. Okay, part B is a little more challenging. I'll give you a hint if you want to repause the video to make another attempt with a hint. The hint is, once you integrate by parts, you have to go through and use a substitution. So integrate by parts and then apply a substitution. We'll check in a few minutes if needed. All right, let's complete part B here. Again, we're going to choose u as the inverse function. That leaves then dv as just dx, leading to v being x. Now, inverse tangent and results related to that pop up frequently throughout Calculus 2. So make sure you're comfortable with the derivative of inverse tangent of x, 1 divided by 1 plus x squared. All right, we have all of our pieces here. We can now take a look at the result from applying the integration by parts formula. And what we get at the very end there is the integral of v du, the integral of x divided by 1 plus x squared. Now that integral hopefully can be easily solved using a substitution. We're going to choose u as 1 plus x squared. All right, let's go through the work on just doing the substitution integral there. Choose u as 1 plus x squared. Du would be 2x dx. We have a factor of x, but we're missing a factor of 2. So divide 2 in the differential statement to get 1/2 du equals x dx. Rewrite your integral from originally being in terms of x to now u, and you should arrive at the integral of 1/2 1 over u du. And we recognize that as being an antiderivative leading to natural log of u. All right, we back substitute, and we get 1/2 natural log of 1 plus x squared. Now be careful, this was used after we applied the integration by parts formula. We still have the uv term, x times inverse tangent, at the top there. So if we combine this back together, we can complete this problem, example 4b, on the antiderivative of inverse tangent. All right, hopefully this one wasn't too bad. Just a little tricky when dealing with one integration method applied with another. Now that we're starting to get into more than one integration method, once we get access to substitution and integration by parts, the difficulty for problems can go up considerably once we encounter problems requiring combining several integration methods. All right, we have one last topic to get to kind of thoroughly cover everything, which is combining integration by parts with definite integrals, integrals that have limits from A to B. Now, it's actually not hard. I have here at the top there your basic, familiar integration by parts formula that we've been using. Now, if we put limits on the integral from A to B, put those same limits on the integral on the right side, the integral of v du, the only part that needs to change is the uv term. We evaluate that from the fundamental theorem of calculus by plugging in the endpoints b and a and then subtracting. Here, u and v are both typically functions of x. So in the uv term, plug in x equals b, plug in individually x equals a, and then subtract that. That's the uv evaluated from a to b term. All right, so a definite integral only modifies the very last part about plugging in limits. It's important to note here, as we have on the screen, that if we have a definite integral, none of the ways we choose u and dv, or those tips or guidelines, change. So we still make the same choices for u and dv, following all those tips and guidelines. It's just a little more work to incorporate the limits. All right, let's close this lecture out with one last final example. Example 5. If you're up for it, pause the video and give yourself an attempt at this. This one, kind of more tedious than difficult probably at this point for you. We'll check in a few minutes. All right, welcome back. Hopefully you were successful. Your choice for u and dv doesn't change due to the presence of limits. We still choose u as the power of x, 2x, and we still choose dv as everything else, e to the negative 3x. Be careful here, as we've mentioned repeatedly several times. Make sure you start incorporating, if possible, the 1 over a shortcut, which we used here. dv is e to the negative 3x dx. We have to integrate that. We get a reciprocal 1/3 factor there, since a is 3. All right, so we apply our integration by parts formula, uv, and then minus the integral of v du. Since v has a negative in it, negative 1/3, that cancels with the subtraction sign from the integration by parts formula. So it is correct there. Notice I have plus. That's due to the minus the integral, and then the sign, the negative with v, canceling out. 2 negatives to a positive. All right, notice the uv term, negative 2/3 x times e to the negative 3x. We're going to evaluate that from 0 to 2. All right, we still have to evaluate the last integral, but if you already applied the 1 over a shortcut for the linear expression inside the antiderivative for e to the x, then we just apply the 1 over a shortcut again to this last integral. We're going to get another factor of negative 1/3. All right, if we combine that, we just have to plug in the limits here. since there already was a 2/3 factor in that last term, we end up, when we integrate that last integral, we get another negative 1/3 factor. So we get a minus 2/9 there. At this point, the calculus is done, and it might, for some of you, actually be harder to actually plug in the limits here, keeping tracks of your signs, than it is to actually apply the calculus above. Now, keep in mind here, we apply the fundamental theorem of calculus by plugging in the endpoints to these antiderivatives. So we individually plug in 2 and 0 and subtract. Be careful, notice each antiderivative term here has a negative in it. Minus a negative would become plus. So just be careful, take time with the signs. Notice in that first term that we're evaluating, negative 2/3 x e to the negative 3x. When you plug in x equals 0 to that, it kills off that whole term. Be careful with the last term being evaluated, the 2/9 e to the negative 3x. There is no factor of x in front of the exponential function. So when you evaluate that at x equals 0, you get e to the 0, which is 1, not 0. So just be careful and take your time, check your signs, and you have some like terms here, e to the negative 6 powers that you can combine together. Here we get our exact value, 2/9 minus 14/9 times e to the negative 6. All right, that completes everything I wanted to cover and typically cover in a standard Calculus 2 course when I cover integration by parts. The benefit of the recorded lecture is you can go back, pause, and take a look at any point as needed.